everyone, welcome to Machine Learning First Steps. Today we'll be working on a linear regression case study, and this course is presented to you by Summer. So what will we do in this tutorial? We'll basically work on a stereo vision depth estimation problem. So what stereo vision is having two cameras like these in order to get the depth of an object. And by depth, I mean the exact location of an object relative to some reference frame. So this stereo vision application just resembles our eyes in a way, because we have two eyes, and this is why we can visualize objects in a 3D fashion. So this is what a stereo camera does. It's basically two cameras attached together. And we're going to work on this problem for an underwater scenario for an autonomous underwater vehicle. So the problem with stereo vision underwater is there's a lot of distortion and refractions due to the water medium. And we need to correct that. So basically, if you deploy your stereo vision camera underwater, the depth estimation results will be very distorted. So we need to use machine learning to correct this depth estimation result. And we're going to do this using linear regression. And basically, we'll be having a data set of true values or ground truth values and distorted values. And we're going to use linear regression to correct the distorted values and develop a model that could actually take the faulty values and correct them and produce values that are very close to the ideal reading. We also implement vectorization using Python for both the cost function and the derivative function. Let's go. So before we proceed with our linear regression case study, we need to present the concept of vectorization. So before we said that the cost function j is equal to 1 over 2m multiplied by the summation of I is equal to 1 up to m. And we have the square of the errors here, which is basically the hypothesis f minus y for individual examples here. And we need to vectorize this because if we want to implement this in a conventional way, we'll use for loops. And for loops are computationally expensive, and they'll just stall the code for a little while. So instead, we apply a vectorization concept. So by just saying that this could be equal to 1 over 2m, and then instead we will use the vectors, which is f minus y. So the vector f here is the hypothesis computed for all values simultaneously and placed in a vector form. And then we're going to multiply this by its own transpose. So we can represent this as the transpose here. So basically, this f minus y vector will have the size 1 times m, and its transpose will have the size m times 1. So the multiplication of these will just lead to one vector or one matrix of size 1 times 1, which is basically the same thing that we need to do. So this will save us a lot of time, and NumPy will help us achieve that in the code, as we'll see later. So let us work on our code right now. I'm going to open up a terminal, Control-Alt-T, and then I'm going to activate my TF environment. And I'm going to open up Spider. And then I'm going to start a new code for my linear regression problem. So I'm going to click New File, and let us just start to code. So first thing I'm going to do is that I need to have a data set of my faulty camera readings, as well as the ideal readings it was supposed to produce. So these will constitute the inputs, or the input features and outputs of my linear regression. So let us type a comment. And what a comment is, it's a statement that I'm just writing for the sake of the readability of the code, in case someone else will read my code, or I need to remember what my code is doing in case I forgot. So I'm going to type a comment, and a comment is not compiled. So whenever the compiler sees a comment, it just ignores it. So how do I type a comment? I'm just going to type hash and then whatever I want right after that hash. So I'm going to say that I'm going to generate my actual z locations, or depth locations, or actual depth data, for example. And I'm going to denote that by z. And I'm going to create a variable called z_actual, for example, which is the actual depth data. And this is going to be a NumPy array. So first of all, I need to import NumPy as NP. So what I'm going to do here is that I need to generate numbers in a certain range with a certain increment, because when I collect my data, I usually use an analog meter and start at a specific distance from the camera, or away from the camera, and then I keep incrementing that distance till I reach the maximum field of view limit of the camera. So let's just say that I need to be at a distance which is between 1 meter up to 2 meters away from the camera. In this case, I'm going to use a function called aRange, which generates that for me. So I'm going to start with 1 meter and up to 2 meters with an increment of 0.01. The reason this is 2.01 is because I'm incrementing by 0.01, and this happens to be my limit. So eventually I will just generate values starting from 1 up to 2 meters with 0.01 meters increment. So if I want, for example, to print that, let's just print z_actual and see how it looks like. So if I print that, yeah, I got what I want, basically. We can see it here, right here in the console. And we need to print the shape of this variable as well. Let's see how it looks like. So the thing is, this variable has a size of 101 times null. And I basically don't like that null axis thing, so I want to make it an actual matrix with a size of 101 times 1, or maybe 1 times 101. So I need to transpose it as well, because I need to have a raw vector rather than just a Coulomb vector. So what I'm going to do here is I'm going to reshape this first. I'm going to type a new line. So I'm going to reshape the z_actual by typing a command or a function called reshape, which reshapes my variable. So z_actual dot reshape, and I need z_actual to be of the size 101 times 1, for example, instead of 101 times null. So basically I need 101, which happens to be the length of my z_actual. So I'm picking shape 0, or a shape of index 0, which means I'm going to pick this 101. And the reason why I didn't hard code it, like type 101 or 101 right away, is because I need my code to be flexible in case I change the range of z_actual later. So instead of having just a hard-coded number here, which is going to most likely produce an error if I happen to change the actual in any way, so let's just keep it flexible like that. And I'm going to add 1 here, so the second dimension is not going to be null. So right now we can print z_actual. It happens to be 101 times 1. And the last step is to transpose that, because I'm going to need it to be a raw vector. So I'm going to run that, and we got 101. And we might print z_actual itself. So basically, yeah, we got what we wanted. So my next step is to generate the data set for the camera readings, which is the output y, basically. Oh, I'm sorry, this was the output y. The actual depth theta is the output y that I'm supposed to get. But the faulty camera readings, which I'm going to generate right now, is actually the input. So I'm going to generate the input. So let's just denote that by y of my algorithm. And let's just generate the faulty camera readings. And we'll call that x of my algorithm. And then I'm going to type I'm going to call that variable zRead, since that happens to be the reading of my camera. And as I said before, that model tends to follow an exponential behavior. So the error in the distance would increase as the distance increases. So I'm going to indicate that this is the exponential of my z actual. And z actual is actually an array or a matrix, and I need to get the exponential of each element in that matrix. So what I'm going to do is I'm going to use the exponential function of numpy. And the difference between that and the normal exponential function of the math library is that this exponential function happens to work with arrays. So basically I'm going to take the exponential of each element of my array. So np.exp, and I get z actual here. So we can print zRead right now, and I'm going to print zRead just to check how it looks like. So basically, yeah, you can find that zRead here is actually the exponential of my original z actual. Need to clear that first. Let us run that again. Oh yeah, I got to print command, so I'm going to delete that because I no longer need it. And we can find that this is the second print statement, which is print zRead, and zRead happens to be the exponential of the original z, or the z actual. So great. Right now I have my data set prepared. So the next thing I'm going to do is I'm going to determine my regression variables. So I'm going to type another comment here. Oops, I didn't save that. No problem. So my regression variables happen to be x, y, and of course the vector theta, which happens to denote my parameters. So I'm going to start with x first. And x is supposed to be the input of my algorithm, which is supposed to be zRead right away, right? But the thing is, my linear function, or my hypothesis, happens to have two parameters, theta node and theta 1. So if I just use theta, if I just use the zRead, I'm going to have to use only theta 1 and not theta node, because theta node is responsible for the bias, and basically it has to be multiplied by 1, while theta 1 has to be multiplied by the z reading elements. So in order to solve that problem, I need to append an array or a raw vector of 1s to the original zRead in order to have that offset dimension I was talking about. So what I'm going to do is I'm going to say x is equal to, I need a raw vector of 1s. So I'm going to say np.1s, which automatically generates a raw vector of 1s, assuming I provide the shape. So I need the shape to be exactly similar to zRead. So I'm going to type zRead.shape. So it's basically copying the same shape of zRead right now. So if I happen to print x, let's print x, we can see that x is indeed a row vector of 1s. So this will represent the offset part of my data. And of course, I need to add, let's just keep the print operation now. I just need to add or append my actual z-read data, which happens not to be the offset, but actually the slope part of theta 1. So I'm going to say x is equal to, and I'm going to use a function called append, np.append, which appends one vector to another in order to form a bigger matrix. So I'm going to append something to x, and what I'm going to append is z-read, and I need to specify the axis to which I'm appending to. So basically, I'm adding one raw vector to another raw vector, which means I'm adding vectors in the raw direction. And I have to specify that axis. So raws in Python take the index 0 while columns take the index 1. So I'm going to specify my axis to be 0 because I'm appending on the row side. And this happens to be my regression input. I'm going to add just a little comment here. Okay, that's nice. We can print x now, and we can see that it's now a matrix having the size 2 times 101. And if we need to make sure or check, let's type x.shape and run, and indeed it's the size we specified. So next I need to determine my regression output, and my regression output has a dimension of 1 times 101 and happens to be z actual itself. So I'm going to type z actual because this is the output I'm willing to get. This is the ideal output or the most ideal outcome I could get because this is the ground truth data. So basically my hypothesis is supposed to be, ideally speaking, is supposed to be y is equal to theta times x. So what I'm going to do here is I need to determine theta. So thing is, we did specify that we don't have an accurate estimate of theta initially. So what I'm going to do is I'm going to initialize it randomly. So I can basically type anything. I prefer to use small values in the beginning. So I'm going to say that theta, and theta is supposed to be multiplied by x. So I'm going to specify it like this, np.array, which is a new array, and I'm going to type this array. So I need it to be of size 1 times 2, basically. So I'm going to type 0.2, for example. You can type whatever values you need here. I'm just going to use 0.2 and 0.3, which are totally random. And I'm going to call this the parameter vector. So let us print theta. Let's see. Actually, theta.shape, just to make sure that the shape is correct. So yeah, it has 1 raw and 2 columns. So the sizes match. And we got that perfectly set. Great. So the next step is that I'm going to start the learning process. And you can notice here that I'm using a fairly simple linear model. So I'm going to start the learning. And for the learning to happen, I have to specify the parameter alpha, which is my learning rate. So alpha is going to be 0.05. For example, it's a tunable parameter. So this value happens to click so many times, so I'm just going to use it. And I'm going to determine the number of iterations that I need to run in order to reach the optimal solution. And this is a hyperparameter as well, so it is tunable. So I'm just gonna pick, for example, 3,000 iterations. Yeah, you can increase it or decrease it, doesn't matter, but these are just values I'm used to, and we can tune it later in order to get better results. So what I'm going to do is I'm going to start a for loop determined by the number of my maximum iterations. Then I'm going to use my formula for theta update, and as we said before, we need this version of the code to be vectorized because vectorized versions happen to work faster than just using for loops for every single snippet of the code. So instead of just using for loops, I need to use a vectorized implementation because it's much faster. So I'm going to type theta as a vector is equal to itself, or its old self, minus alpha times the derivative of the cost function with respect to the vector x, the vector y, and the current theta. So what I'm going to, actually the derivative with respect to theta, but I'm going to include x and y as inputs to that derivative because it is dependent on all of the three variables, but the derivative itself is with respect to theta. So let us just assume that I have some function that could calculate this derivative for me, and it takes theta, x, and y as input arguments. So of course the code is displaying an error here because I have no function called deriv. So I'm just going to assume that it exists. And what I'm going to do next is that I'm going to try to develop that function basically. So I'm going to somewhere here and I'm going to create my function. And as opposed to system-wide sort of functions like in np.arange, for example, where I have to include a library and I'm just going to use that special feature, I'm going to create the function myself. So we're going to learn how to basically write a function. So what I'm going to do is type def, which means define, and this is the name of my function, deriv, and take three input arguments, theta, x, and y. Now I'm within the scope of this function, so this function will only execute if I call it. So it's a special type of code which executes only when I call it, so it doesn't have to execute, right, basically. While the rest of the code just executes normally once I hit the run button, this derivative function will not be executed unless it is called. So I'm going to first determine the number of examples, m. So m happens to be 101 in this case, so it's x.shape 1, which is the number of my training examples. Which happen to be the second dimension of x as well, so I'm just gonna determine it using that expression. And I'm going to calculate the derivative. So let's just denote the derivative as a variable by dj, which means the derivative of the cost function. So I'm going to use the vectorized version of my derivative expression. So that's going to be 1 over m multiplied by the matrix multiplication of the hypothesis function. And as a matter of fact, I don't have this hypothesis function yet, so I'm going to create another function that calculates this hypothesis, and I'm going to assume that this function does exist. So I'm going to call this function hypo, for example, and it's going to take theta and x as input parameters, and this hypo has to be or actually y has to be subtracted from that hypothesis. So I'm going to add minus y. And we know that we have to multiply that by the transposed version of x. So this is going to be x transpose, which basically denotes the byproduct of the derivative process. And I'm going to close that. Oops, we have a problem with the dimension. So yeah, I think we need to add a bracket here. So yeah, I think we're good to go. Yeah. Right. So what this function has to do is to return that variable dj to the original code to replace this deriv expression. So I'm going to type a keyword called return, which returns that variable, and I'm going to say dj. So what's going to happen, still have an error. Oh yeah, the hypo is not defined yet. All right, no problem. So what my function is going to do is it's going to send dj to replace that expression. So basically what happens here is as follows. Theta is equal to theta minus alpha times the returned value dj. This is how it's going to work. So first of all, before running this, I need to determine this function hypo, or define it. So I'm just going to define another function. So let's just say define hypo, which is the hypothesis, and it takes theta and x as input arguments. And I'm going to denote the variable by f, which, for example, f of x. So np.matmul, because I need to multiply theta times x, which both happen to be vectors. So this is another vectorized implementation. And I'm going to return f. Oh, sorry. Right? So basically when the ref calls this function hypo, what's going to happen is that this part of the code will execute and just return a copy of f here. So this is going to be f instead of just this expression, hypo. Alright, so I think if we run it, we can just run it to check that there are no errors. And we can check the variable explorer here. So actually our code ran and just selected these theta values. So these are considered to be the optimal theta values after the execution of my code. So we need to verify that visually in order to determine if that is right or that's wrong. So what we're going to do is we're going to import the plotting library, which is matplotlib, which is called pyplot basically. And I'm going to import matplotlib.pyplot, which is a very long name. So I'm going to import it as just plt, short for plot. And by the way, if you don't have this package or library installed on your environment, you can do so by just typing conda install pyplot in your terminal. So you can open up a new tab here and install it, and then just continue your good work. And if it is available, I'm not really sure if it comes by default with conda, but in case it's not available, you can just install it, same as we did before with NumPy. So next step is I need to plot some information in order for me to determine if things are running well. So I'm going to type a comment, which is the result plot section. And what I need to do here is I need to plot the corrected readings versus the faulty readings, as well as the ideal readings versus the faulty readings, in order to obtain some estimation of how these functions or how the hypothesis matches my ideal output y. So I'm going to say plot the plot There are two different plots. One is an abbreviation, the other is a complete plot word. And I'm going to plot zread, but actually the plot function needs only one axis at a time, or takes one axis at a time as an input argument. So I need the basic raw vectors. Basically, it takes a vector of the dimension something times null, or null times something. So in order to do that, I'm just going to include the 0 index for raws, which means the very first raw. And I know we already have 1 times 1 on 1, so basically it's one raw, but still we have to determine that first raw because it just treats zread as a matrix currently, and it needs just a vector instead of a matrix. So it's quite the opposite to what we had here, because here we needed to, in the beginning here, we needed to convert that from the null axis convention to the matrix or the full matrix convention. Here we need to do the opposite, so I'm just going to take the very first raw and all the columns, and the expression all the columns can be just done by typing this. So basically this sign here means take all the columns, or it makes all, it means all basically. So if I write it in the raws, for example, it means take all the raws. But then it won't make sense to take all the raws and all the columns and all the columns, because that would be basically zread itself. So I'm just going to take that, and if you want to print the shape of this expression I got here, so let us just print that and print the shape of it. Let's just comment that because this is not an incomplete line. So I can run that, and you can see that now we have an array which is 1 on 1 times null. So I need to get it back to that convention in order to plot it properly. So we have the x-axis, which is specified to be zread, and for the y-axis I'm going to type z-actual, 0, and all as well. And I'm going to give a label for that line because I'm going to print multiple lines, so I'm just going to say that this label means the original data, which means z-actual, which is the original or ideal output. We can call it ideal as well. Alright, we can call it ideal instead, maybe. What we need to do now is to also plot my algorithm's performance in order to compare it to the ideal situation. So I'm going to just copy that line and let us change things step by step. So I'm going to have the same x-axis, but I'm going to change this to be my hypothesis. So what I'm basically going to do is that I'm going to call the function hypothesis using my ideal theta or optimal theta along with my input x. And same thing, I need to include the very first raw vector. And the label, I'm going to pick another label, so I'm going to call that corrected, which means the corrected variables or algorithm performance or whatever. And let us just give a label to the x-axis and the y-axis. So let us just give the x-axis the name. We can call that faulty camera readings, and since the x-axis happened to be zread, which is the faulty camera reading, and the unit is meters. And we're also going to plot the y label, so let's just copy that and change things step by step. So I'm going to plot the y label here, and let's just call this the desired output, whether it happens to be the corrected or the ideal, because they're both desired outputs. Or we may just call that output, because actually we desire the ideal situation, but the best we could get is a corrected version, which is very close to the ideal situation. So I'm just going to call this the output in meter. And last, I'm going to show this plot. So I'm going to use show in order for the plot to show up. So let's run that. So we don't have any errors, but if you check the plots tab here, you can find that there is a new plot that was shown up here. So basically, we can find, line labels are not showing up, which is weird, no problem. So anyway, you can find that the original y values are plotted on the blue line, which happens to be the ideal case. So basically, it's like the inversion of the exponential, which happens to be like something that looks like a length function, for example. And we got our linear prediction line or our hypothesis, which sounds very close to the ideal situation. But since we're using a linear function, this is the best we can get because the original function or the ideal function is nonlinear. So the best linear line that we could get is that one. So it's not very accurate, but it's the best possible outcome that we can get, given that we're using a linear function. So we can use the trick of the nonlinear parameterization, or the nonlinear converted to linear trick, by maybe adding, for example, this function. When you first look at it, it just looks like something like the square root or some root of the original x. So we might actually append some other features or new nonlinear features. Like, for example, we can say, we can append something like, here just appended the x. So instead of appending x, we can append the square root of x actually. So mp the square root, for example, x. Sorry, I don't need to say that. And we can actually append more features. Like, for example, rather than just relying on the square root, which is the power half, we can also rely on the power third and power quarter, and so on and so forth. So we can append more features. We can just, right, we can say, for example, np to the power x, and we're going to give it the power, here we got half, let's just say third, for example, over 3 maybe. And let us just keep appending things. So let us append another nonlinear feature, which happens to be 1/4 maybe, and maybe 1/5. So we got more features, and the more features you have, the more your curve more accurate your curve gets. So let's just say 1/5, and now we have 1, 2, 3, 4, 5 features instead of just 2 features, and one of them happens to be the offset raw, which is basically ones. So I'm going to include more variables here, more parameters. 1, 2, 3, 4. We need one more, so I'm just going to point to 1. So yeah, basically now the sizes match. And we can run that again. Let's see what we get. Oh, actually, yeah, I think I made a mistake because, oh, the power function is also it just used MATLAB, so I may have confused that for MATLAB. So let us just okay, power function in Python, because I forgot that. Actually, yeah, we got a power thing. But let's just say numpy. Oh, it's power like total power, not just POW. So I'm just gonna say power. Seemingly, POW is only used for the math library, but for NumPy it's power. So let's just run that. And we happen to have another curve which slightly has a better curvature maybe, because we can see that this is slightly more curved than our last variable or our last function. And we got thetas here, different thetas. We can vary the hyperparameters as well, like including, for example, 10,000 iterations instead of 3,000. Let's run that. Oh, it's basically the same thing. Didn't change a lot, so I think 3,000 is just enough. We might try, let's just delete that one because it's the same as this one. So we actually might try to append a new nonlinear feature, because since the original z-read or the camera model is kind of exponential, so let us just use something like that. Let us use a feature that is the inverse of the exponential function, which is basically len function maybe. So let us add one more feature here, maybe. That happens to do with the len function, and I think that is going to be impeded log, because the len function is called log for some reason in programming languages, which is the natural logarithm. So let us just say natural log function in NumPy. I think it's impeded log. Yeah, indeed, it's impeded log. So we've got impeded log x and z-read. Actually, I think I made a mistake here. Yeah, I think I made a mistake because I was not supposed to add the square root of x. Instead, it should be z-read instead of x. Because here we got the ones and we got to append the square root of the readings, I guess. Yeah. So maybe that was what caused the error in the first place, because here x has changed, so I can't change what has already changed. I need to change the original thing. Okay, so basically here I appended z-read, and I need to append, I think, yeah, I did the wrong thing here. I was supposed to append things to x. Yeah, that's a bug and it happens. But alright. So I'm appending new raws to x, and I'm going to change this to be, for example, z-read. So np dot power z-read half here, maybe, because that's the square root. You can just type the square root, it doesn't matter. And this is actually, well, we don't need this line anymore, right? So I'm going to append the power of z-read to have, and yep. So I'm going to change these as well. And let us just type 1/3 maybe. And let us append maybe 4 here, and let us append one more feature, 1/5. We no longer need the raw z-read thing. And this last one doesn't make any sense, as we said before, so this is basically our regression input now. So what we did is that we first added the feature, like the ones feature, ones row vector, which is the offset part, and then the slope part, which happens to be related to theta 1, theta 2, theta 3, and so on. So basically we got a new raw, which is the square root of z read, and we got power to 1/3 and power to 1/4 and power to 1/5. All right, it's supposed to work now, and we got y is equal to z actual, and we have 1, 2, 3, 4, 5, so 5 features, and 1, 2, 3, 4, 5 thetas. So let's run that, and actually, yeah, the results improve. Now we can see the curvature a little bit better here. I'll just delete that. That was a faulty one. So basically, we had this linear function in the beginning where we used just linear combinations of input variables. Now we have nonlinear combinations, and the results are just getting better. So we can make it better and better, maybe by including a len or a natural logarithm. So I'm going to copy that. And let's just say here that we need np to append x. Let's append np.log of z read. And let us just remove that fifth part because that's the natural logarithm. And yeah, let's try that out. Let's see how it turns out. There is an error. Okay, maybe there's something wrong here. Maybe it has to do with the z-read. I'm not really sure. I'm not following this. So let's try to type that expression alone, maybe. And yeah, it sounds fine by me. Oh, I forgot to add a new theta. I forgot to add a new parameter because we have a new feature. So let us just say 0.33, something like that, right? So let us run that, and actually the curvature is improved right now. So basically we got two functions that are almost overlapping. So basically we started with this, and we started to add some nonlinear combinations consisting of roots, basically. So we got that, which is slightly better, and then this, which is much better. So basically, you have to have some intuition regarding your nonlinear combinations, because if you got good nonlinear combinations as input features, you'll basically get better results, and your functions will start to overlap just fine. And this basically means that our hypothesis, which is our prediction, happens to have a very small error with respect to the original ideal function. We can actually try to plot something else, like the cost maybe. So let us define a function that computes the cost. So let's call that, for example, let's define a new function, and let's call it define cost, and it's going to take theta and x as input arguments, and as always I'm first going to compute the number of training examples, so we can copy that line. And we are going to compute j, for example. So let us just say j is equal to 1 over 2m, and that is going to be multiplied by the sum of the different hypotheses. We can actually maybe do this, maybe. In p.matmul, try to provide a vectorized implementation of that, which is basically the hypothesis, which is this part, and we can remove the extra brackets here. And so we're going to multiply the hypothesis by its transpose, basically. And we know that the hypothesis has a shape of, let's just check the shape of the hypothesis. Shape. So it's 1 times 1 on 1, great. So what we need to do is to multiply this hypothesis by its own transpose here. So let's just copy that and dot t. Yeah. So we got 1 over 2m multiplied by the sum of the squares. So basically, you got the hypothesis. We also forgot to minus y because that's supposed to be the error. So minus y here. And the same thing goes for this one because we need to calculate the error and then calculate the error for each example. Then square it, which is equivalent to the multiplication of these, then sum everything. Yep. So this is basically the correct vectorized implementation. And we've got all of that multiplied by 1 over 2m. So what we need to do now is to return j, which is the cost. So we can, for example, print the original cost here. So let us just print original cost before optimization. And basically we're going to compute j. So we're going to compute the cost with thetas that are not yet optimal, not optimized. And then after our algorithm is concluded, we might print the same statement again, but this is optimized cost now. So optimized cost is, well, same expression. Sorry. Let us run that. Yeah, and you can find that the original cost is very big compared to the final cost. I mean, here we got 1.14, and then we got 2 times 10 power negative 5, which is pretty low. So that means our algorithm works fine. So that's it for our code. This is our first machine learning application, which happens to be a simple problem, yet very effective. Yet has a very effective solution. So in order to summarize, now we understand how linear regression works, and we successfully implemented linear regression on a stereo vision depth estimation correction case study. So congratulations, this is your first machine learning project, and we'll go through more case studies as we proceed throughout the course.